Good evening, everyone, and welcome to the 6th Zoom into Physics run by the Australian Institute of Physics. Let me start by acknowledging the traditional custodians of the lands on which we meet. For me, here in DY, it's the Darug people, and we're very close to the ocean here, and I pay my respects to their elders, past and present. Let me give you a little bit of an introduction to the AIP. It's the Australian Institute of Physics. It's Australia's peak body of professional physicists, and our role is to protect and promote physics in all of its various forms to all of the people who are interested and influence physics in Australia and around the world. Just to give a little bit of a plug for our next exciting event. It's the event formerly known as Physics in the Pub. There won't be much pubbing involved, and so it's now Physics in the Cloud. It's on Friday the 15th of October at 7 p.m. And there's a link already in the chat for people who want to get that, or just go and visit our meetup page. Some of the attractions for that evening, we've got Chris Ferry, famous for quantum physics for babies, and lots of other wonderful titles for babies. We've got the CSIRO photon fanatic Rachel Rayner, and she'll be talking about being on the spectrum, like electromagnetic spectrum. And we've also got talks on aeronautics, laser-guided spacecraft, seismology, archaeology, and to top off the evening, our very own philosopher in residence, Tibor Molnar, will argue that stuff doesn't exist, and that if you did happen to enjoy the evening, that you couldn't possibly have because it didn't exist, and neither do you. And also that the hangover that you'll get the next morning will also be a figment of imagination of someone else who might exist. And so check out that on the AIP website. I'm dreaming for the day when Physics in the Pub goes back to the pub, because for me, it's really not quite the same without a pint of beer in your hand. Also on the AIP website is a link to our Zoom into Physics site. It's aip.org.au/ZIP. So check that out and you can find all of our previous videos there. And I can announce today that last month's video that we did here is now officially the AIP YouTube video with the highest number of views in the history of the universe. And perhaps it was due to the teaser image I used of Tamara holding a box of dark matter. And maybe we've got some merch opportunities there, I think. Although I should say, please buy your dark matter from the AIP. Definitely do not buy it from Tamara, because I've heard that she cuts her dark matter with neutrinos, so you're not getting the real deal. So how does it work tonight? Well, the only strict rule that we have is that we finish around 9:30, and how we get there is really up to us as we go along and just have a bit of fun. We really like this format because it allows you, the participants, to participate. And you can do that in two ways. Just unmute yourself and ask a question, or pitch in, or use the chat function. And normally there's a couple of parallel conversations going on, one in the video and maybe 2 or 3 going on in the chat. So please remember to have a go with that. Also, we do record the chats, so that if you do have questions or suggestions, please put them in there and I'll be able to read them later and distribute them amongst the panel. It's acceptable for you to enjoy drinks or nibbles, and feel free to cuddle your cat if that's your thing as well. Anything goes, pretty much, as long as it's clean and courteous. So what I will do now is introduce the panel, and they will be asked to say a little bit about themselves, but also to answer the introductory question, which is following on from last month. What surprised you most about the dark matter and dark energy discussion during last month's Zoom meeting? So without further ado, let's kick off with Kirrily.
Hi, good evening, everybody, and thanks for joining us. So I'm Kirrily Rule. I am the Honorary National Secretary of the Australian Institute of Physics. I'm a physicist by trade, and I'm an experimentalist. So I'm a little bit out of my depth here when talking about dark matter and dark energy and things out in the cosmos. I look at things on more of an atomic scale. So I'm a neutron scatterer, and I work at the Australia Nuclear Science and Technology Organisation, or ANSTO. And to answer your question, Scott, what was I blown away with from the last session? So I think whenever I was conceptualizing dark matter, I was always thinking about it as being a long way away. It's out in the galaxies. It's out at the edges of the universe, which are expanding at an accelerating rate. I never imagined it so much on Earth until I saw Geraint show us his little hands and say there's dark matter in his hands. That's right. And then Tamara came up with her box. How fascinating was this box? And then Ray said that we've got experiments being built deep underground in Stall. You know, this is amazing. This stuff is all around us. We just can't see it. We just don't know. So that's something that's fascinated me from last time. Thanks.
Thanks, Kirrily. Geraint has just said in the chat that he's published a book with Chris Ferry. So I'm going to hand over to Geraint, and he can tell us about that. Look at the book and a bit about himself.
Okay, thank you. Yes, so I'm Garrett Lewis. I'm a cosmologist. I'm based at the Sydney Institute for Astronomy, part of the University of Sydney. And I just mentioned in the chat that a book I've written with Chris Ferry has just been published in the US called Where Did the Universe Come From and Other Cosmic Questions, where we look at how in understanding the universe, we need to understand the physics of the very large, which is gravity and Einstein's general theory of relativity, and the physics of the very small, which is quantum mechanics. And that book is not a book for babies, but we hope it's a book for at least smart children and above who want to understand how the universe works. To answer the question about what did I learn the most from the last session, so I guess myself and Tamara and Ray, we're in a weird place, right? We live and breathe, and our day is spent with trying to understand the dark universe, the dark matter and the dark energy that's all around us. And I guess I'm always somewhat surprised, and I know it's my blinkered view of the world, that not everybody in the entire planet is not obsessed by this problem about this dominant stuff in the universe, this dark matter and dark energy. There's much more of it than there is of us. It outweighs all of the stars and all of the galaxies and all the stuff that we can see by a long, long way. And for me, as an astronomer, it's one of the things that keeps me up at night, is worrying about that dark side of the universe. So yes, I think it's a big problem, and I would like the world to understand how big of a problem it still is for us to understand it.
Thank you, Geraint. And finally, for our permanent panel, he may or may not exist, Tibor.
Thank you, Scott. I'll materialize just for this evening. I'm Tibor Molnar. I'm a philosopher of science. I'm an associate of the Department of Philosophy at Sydney University. And I'm fascinated by all things scientific, and no less by dark matter. What I found most fascinating from last month were two things. One of them is that I did learn an awful lot about dark matter, more about what it isn't than what it is, perhaps, but I certainly learned a lot. And yet at the end of the evening, I was still as much in the dark as I was when I started. So it's fascinating. It's impenetrably difficult to get your head around things that somehow are tantalizingly there but aren't. It's mysterious. The other thing that I thought was absolutely fascinating, Ray mentioned this, was the concept of dark matter and dark antimatter annihilating to create dark radiation. The concept of dark radiation never occurred to me. I thought, I'm going to try and find out. I must find out what that could possibly be. That sounds like one of those things that really doesn't exist. So I'm hoping we can clear up some of that today as well. Thanks.
Fantastic, thank you. And now to our pan-dimensional professors, guests on this dark matter subject. Tamara, can you tell us a little bit about yourself, please?
Yep. Hi, everyone. So my name's Tamara, and I actually study dark matter and dark energy and stuff as a living. I'm at the University of Queensland and really enjoy going out and looking for things like exploding stars, supernovae, mapping the distribution of galaxies in the universe, looking at supermassive black holes, and putting all of this information together to understand what dark matter and dark energy could be, or at least how they behave. And I guess for the question from last time, like Geraint, I've got a lot of, I am accustomed to thinking about these things all of the time. And so it's always fascinating to me what level of skepticism other people bring in and what people find convincing and what people don't. And it's not always the same as what I would find convincing. And one of the things that I find most convincing about the evidence for dark energy and dark matter are just the wide variety of ways in which they've been detected, and all coming together to make this big complete picture of something being there that we need to explain, and yet we don't know what it is. And we don't know whether it's a thing or the need to change our theories.
Thank you, Tamara. And finally, on our panel tonight, Ray Volkas.
Well, hi everyone, good evening. Thanks for attending. My name's Ray. I'm a professor at the University of Melbourne. I'm a theoretical particle physicist. I'm also a chief investigator on something called the Australian Research Council Centre of Excellence for Dark Matter Particle Physics. So this is a 7-year program that is trying to do its bit to uncover the nature of dark matter, or perhaps just to prove what it isn't. My job is, I'm really a model builder. So what I like to do is invent new theories. I like to take what we know about the universe now and extend our knowledge by sort of thought experiments about what the next best theory could be, and especially in the context of this session, how the theory can be extended to include a viable candidate for dark matter, and then to understand what sort of experiments or observations would need to be done to establish that theory at some level or to disprove it.
Thank you, Ray. Before we start off, I'll just launch this poll. It's a very simple poll about where you sit in the spectrum of expertise, going through from casual interest at one end of the spectrum to it's my job at the other. And the other thing, while we're doing that, can I invite you, if you were here last session and you have a question, please feel free to launch into that right now, either in the chat or in person. And indeed, if you're new this time, if you have a burning question about the topic, please launch into that. So we've got, all right, I think we're almost done with the poll. We have 29 people, and I will share the results there. 59% of us have a casual interest, and then it decreases not that fast to 10% saying it's my job. 3, hang on, that's the same number of people who are panelists in that area, so that's correlates. Cool. At least it's not 2. So there is a question that's come through. And the question is, if matter is dark matter, if matter is dark matter, it also related to dark energy. So I guess the question there is, I think, is how are dark matter and dark energy related? That's a good question to kick off with. Who would like to field that one?
I'm happy to if no one else wants to chip in. As far as we know, they're separate issues. We call both of them, we use the adjective dark for both of them, but they seem to do quite different things in the evolution of the universe. So dark matter is very important for understanding how the very smooth early universe after the Big Bang evolved into the sort of clumpy universe we see today with galaxies and stars and so on, and important for understanding the dynamics, the motion of things like galaxies and clusters of galaxies today. Whereas dark energy is about the fact that observations show that the expanding universe is actually accelerating in its expansion rate. And it doesn't, at this point, there is no evidence at this point that whatever the dark energy is clumps in the same way as dark matter. So they do seem to be quite different things. There are some speculations they might be related or they might interact with each other in some way. But really, as far as we know, they're quite different things, but both of them are mysterious.
Thank you. There's another question from Neil. Given the dominance of dark matter versus real matter, ought there not be a lot more fuss made in the real world? If 1 in 20 people had even heard of it, I would be surprised. So I guess that's a question of awareness rather than the matter of physics.
Mm-hmm. I guess you can argue that you know, since we can't touch dark matter and it really is negligible in terms of the gravity of the Earth and the stuff that you interact with in your everyday life, ought would be a strong word. It's very understandable that people don't know about it, and indeed we didn't know about it as a human species for a very long time until quite recently. So it's not surprising that it's not well known, but you know, of course, since it's something that I'm sure everyone on the panel finds very interesting and is, you know, important to our understanding of the fundamental physics, where we came from, how the universe began, how it's going to end, how did we get here, all of those types of questions and considerations of what's the next theory of gravity going to be, how do we reconcile gravity and quantum physics and stuff. It is a really important thing to understand. So I like the enthusiasm that we should get more people to understand it.
Yes, importantly, it's not part of our everyday experience. So you're only going to find out about it. The people are only going to find out about it if we physicists tell them, or they happen to be studying something at university, or they go out of their way because they're really interested to find out more about how the universe works. But it's certainly not going to come knocking on their door and say, by the way, here we are, we're dark matter, look at us and work out what we are. So it's a very strange substance, very strange something, it may not even be a substance. It's a very strange influence or effect on the world, and something which is beyond most people, or I would say everybody's experience.
I mean, I think we should add that, of course, this is a mysterious part of the universe that we know that we don't yet understand. And there's a famous story, it might be apocryphal, I might have the people wrong, but when Faraday was showing sort of the first electric motor or electric sort of circuit to a minister, and the minister said, well, what's this for? And Faraday's response was, well, one day, sir, you may tax it, right? We do not know what the physics of dark energy and dark matter is going to lead to, which is why, you know, blue sky science is important. It might be unknown to people now as electricity was to people 500 years ago, but in 500 years, we might have dark matter engines or something within our house. We just don't know.
Mm-hmm.
Can I chip in with something? Because I forgot to answer one of Scott's questions, which is what I now found most surprising about the discussion last time. And it actually relates to something Tibor just mentioned about the ineffability of dark matter. The thing I found most surprising was actually a discussion towards the end, rather brief discussion between Tibor and I think another philosopher about something called instrumentalism, which is the fact that we learn a lot about the universe, not directly through our senses, if I've understood correctly, but through our instruments. And then our senses, of course, interact with our instruments. So to what extent? So I was sort of surprised by the fact that this causes puzzlement or angst or some sort of term.
Mm-hmm.
Yeah, it's not really puzzlement. That was Peter Farley, a PhD candidate, I think, at Sydney University. I know him well. And we were actually saying that instrumentalism, or I was saying at least, that instrumentalism is the way of science.
It is, yes.
I mean, our eyes are instruments, our ears are instruments, everything is an instrument which detects the world. And then it is from those detection events that we make inferences, abductive inferences, as they're called in philosophy, where you try and reverse engineer your inferences to try and work out what the hell caused them. And I think that's what we do. That's what science is. So yes, science is all about inference. And as I said last month, I'm perfectly comfortable with that. But it does surprise people. People have this expectation. The wide audience, I think, has the expectation that science has somehow direct access to the facts, and that the science either is a fraud because they don't know anything, or they have access to the facts and they know everything and they're out to get you. But there are all sorts of strange attitudes towards science, whereas in fact, really it is a game of inference.
Okay, thanks for
and
that.
interpretation.
Yeah.
I think one of the cool things about, or one of the reasons that we would like to have more people consider things like dark matter and certainly astrophysics in general is to understand, get a sense of perspective of where we are and what we do. It's like when you look at how precious the Earth is and how, you know, it's that pale blue dot classic quote from Carl Sagan, where you, if you look at the Earth sitting in space and look at this like tiny little sliver of atmosphere, which is what is keeping us and everything on the planet alive, in the context of the big empty universe and stuff, your petty squabbles with your neighbor or some country rivalry or something just seems to make no sense whatsoever anymore. And I think it's a really important perspective that we can give people by getting people to expand their minds about beyond, you know, what TV show they're going to watch or what piece of clothing they're going to buy and that kind of thing.
Here, sometimes I like to say that I think many people live their lives pretending the rest of the universe doesn't exist.
Way to make me feel so insignificant now. Thank you.
Okay, let's start off with a question here that we have. What is the relationship between dark matter or the dark matter field and the Higgs field? Does the Higgs field also determine the mass of dark matter particles?
I think that one's for me. So first of all, just to say a few words about the Higgs field for people who are not familiar with it. So there's the Higgs field and then there's the Higgs particle. And the Higgs particle was discovered in 2012. And the Higgs particle represents an excitation, a kind of wave on top of the Higgs field. And the Higgs field is a funny kind of, I'm tempted to call it a force field, but it's not quite a force field, but it's something like that is supposed to permeate the entire universe and have the same value throughout the entire universe. And particles like electrons and quarks, the elementary particles of the standard model of particle physics, when they move through space, are also moving through this Higgs field. And they interact with the Higgs field, and that's how they acquire mass. So the fact that the electron, you know, which moves around in wires and gives us electricity and so on, the fact that that has a mass, according to this very well-tested theory, the standard model of particle physics, is because it interacts with this Higgs field. And if the Higgs field wasn't there, electrons would be massless, quarks would be massless, the entire universe would look nothing like the universe we live in. So the Higgs field is very important. And as far as we know, it is almost the universal source of mass for the known particles, by which I mean the particles of ordinary atoms and then various unstable, heavier particles like muons and so on that we also know exist and we can study in accelerators. So the question is this Higgs field responsible for the mass of everything or only of some things? And in particular, is it responsible for the mass of dark matter? Now, I would say it's very unlikely to be responsible for the mass of dark matter, because we know that the dark matter interacts extremely weakly. That's why we call it dark. And if the Higgs field was responsible for giving it mass, that would mean the dark matter was kind of more similar to ordinary matter than it should be. It would go against the observation that dark matter interacts very weakly with ordinary matter. So I would say the answer is no. It's very unlikely that the Higgs field has much to do with the mass of dark matter. I mean, it could have something to do with it, but I'd be surprised if it was a dominant source. I'd also point out one more thing, which is that not all the mass in the universe that we know, ordinary atoms, is due to the Higgs field. For example, the mass of the proton, the mass of the atomic nucleus, the mass of the neutron, that has got very, very little to do with the Higgs field, because neutrons and protons are bound states of elementary particles called quarks, and the quarks interact with each other very, very strongly, and they're confined into this tight balls that we call protons and neutrons. And the masses of those particles, which is basically responsible for most of the mass of ordinary matter in the universe, is due to the energy of the binding of the quarks into protons and neutrons. The Higgs field is responsible for the masses of the quarks inside the protons and the neutrons, but those masses are known to be tiny compared to the masses of protons and neutrons. So even if we're talking about most of the ordinary atoms in the universe and where they gain their mass, the answer is actually not the Higgs field. It's the binding energy and the kinetic energy of the quarks and the gluons that are binding neutrons and protons. So I think how dark matter gets its mass is a very, very, very deep problem. And one of the things one of the facts that we know that I find fascinating and is a sort of starting off point for a lot of my research is the fact that the mass density of dark matter that the cosmologists and astrophysicists have measured is not that different from the mass density of ordinary atoms. It's actually about 5 times bigger. It's not 10 to the 5 times bigger, or it's not 10 to the 5 times smaller. It's a number of order 1 times the mass of ordinary matter. So to me, that suggests there might be a connection between the origin of mass of ordinary matter and the origin of the mass of dark matter. But the origin of the mass of ordinary matter is not the Higgs field for what we're talking about. It's actually the mass of the proton, which comes from something completely different. It comes from strong interaction physics. So I think this is a bit of a complicated subject, but I think it's actually a very deep problem in speculating about what the dark matter might be, to understand why the amount of it by mass that we see today is so similar to the amount by mass that we see of ordinary atoms.
Do you think there might be an argument that since a lot of the mass in the normal matter comes from binding energies, not the Higgs field, and there's a lot of mass in dark matter, that maybe that could be used as a piece of evidence for interactions?
Yeah, exactly. I mean, this is the kind of thing I work on in my day job. Dark matter could be, for example, a kind of dark neutron. So a neutron is one of the constituents of atomic nuclei. It's an electrically neutral particle. It's unstable. It has a lifetime of a few minutes. But in an alternative, you can imagine modifying the physics of neutrons a little bit and making them stable, but still being bound states of things like quarks and there being strong interaction dynamics. So it could well be that the dark matter is something similar to a dark neutron, something similar to a neutron, which we could call a dark neutron. I think that's a possibility. I think it would take a lot of hard work to establish that, but I think that's an interesting possibility. It's not the most common, idea that physicists think about as dark matter candidates, but I think it's well motivated and quite respectable.
That raises for me a rather left-footed kind of question. If the particles of the standard model acquire their mass through interaction with the Higgs field, and I kind of understand how that might work. I can imagine perhaps the viscosity of the Higgs field or something, creating something that we might call mass in particles. Where does energy get its mass? And what do we mean when we say energy has mass? Because energy is not the same kind of particle as the bosons are not the same kind of particles as the fermions. What do we mean by mass? And do we always mean the same thing when we talk about the word mass in physics?
Well, for myself, when I write down equations, I know what I mean when I say mass. It's the m in my equations. so a bit. I mean, but what kind of answer are you looking for there with regards to what do we mean by mass?
Well, one of the issues that I'm thinking about is that it would seem that the property of mass that is, or an electron's mass is not a property of the electron per se, but it's a property of the interaction between the electron and the Higgs field. So it's not actually a property of the electron. Now, is the mass of energy then not a property of the energy, but the property of the relationship between energy and something else? Exactly what are we attributing the mass to when we talk about the mass of energy?
When you're talking about the mass of energy, you mean just the equivalence of E equals mc squared, the fact that there is an energy that corresponds to a particular mass. Is that what you mean?
Not exactly, because as Ray was describing it, the mass of a proton or the mass of a neutron is largely the binding energy that binds it together. So it's the energy there. They're not mass equivalents. There's now energy there in the middle of the proton, which makes up 99 point something % of the mass of the proton, because the quarks are very light. They're very small.
Well, I mean, it's not just binding energy, it's the kinetic energy of the things moving around as well. But, you know, E equals mc squared is saying there's an equivalence between energy and mass. So all the kinetic energy and binding energy of the quarks and gluons inside a proton and neutron, when you measure a proton or a neutron, manifests as its mass. So energy and mass are interchangeable concepts.
I guess one of the other aspects is mass is related to how hard it is to move something.
Yes.
So the difficulty with how much you have to push a proton to make it move is not just the mass of its constituents, but the contribution that comes from the energy. So I guess that could be that's what we mean, I guess, by mass, is sort of how hard is it to push something. Would you others agree with that?
Well, I was going to say that physicists this is one of our dirty secrets, right? Is that there's not a single definition of what mass is. We have mass as the amount of stuff in an object. We have mass as in how hard is it to push something. And we also have mass as what is responsible for a gravitational field. And we often just write m in equations, and we just say, oh, these are the same thing. But there are people who have done experiments to show that inertial mass and gravitational mass are the same. And these are open questions about why some of these things do come out to be the same things in our equations. So yeah, this is why answering the question about energy and mass is not a straightforward thing, because we have to understand what you mean by mass when we answer it.
Yeah, it requires a subtle discussion. In fact, Geraint reminds us of an important point. I mean, if you've studied, Newtonian mechanics at high school or university or wherever, you will remember that there are those two versions of mass. There's the inertial mass and the gravitational mass. And as far as Newton's theory is concerned, and observationally, these things are proportional to each other or equal to each other, as the case may be. And this is completely mysterious, completely unexplained in Newton's theory. And in fact, it was one of the starting points, the most important starting point, I guess, for Einstein developing the general theory of relativity. He wanted to explain why these two different versions of mass are actually the same. And that's how he came up with his geometric interpretation of what gravity is, which Geraint and Tamara can talk about more knowledgeably than me. But yeah, I mean, thinking about mass requires a lot of subtlety, and sometimes you get very deep things out of it, like general relativity.
And perhaps that's the point of this whole conversation. I think it's important for everyone to realize, not necessarily for us physicists, we know what we mean, as Geraint says, but it's necessary for the general public to understand that mass is, again, as Geraint says, it's different things, and we use it to mean a range of things that we don't always mean the same thing. And as you say, Ray, it's subtle. But concepts in physics are not as simple as a layperson understands. And even as a high school graduate understands, because in high school, you do get told a lot of porkies about what mass is and what Newtonian physics is, because it's a simplified version of the story. And later on, you discover that none of that's true. It's all somehow else.
Yeah, it took me years to understand F equals ma, Newton's second law. When I learned about it in high school, I didn't know what they were talking about, because you understand what A is, but then you're introducing two things you don't understand, M and F, in the same equation, and you're saying they're related to each other. So I didn't get that at all. It took me a while to, and it goes back to Newton. I'm afraid he expressed his laws in a rather unclear manner, and there is a way to express them properly, but you have to look at a rather more modern book.
Yeah.
So let's go back to the question that Tibor rose in his introduction, and that's dark, I think, positive and negative dark matter annihilating to create dark
Radiation.
Yeah, I mean, that sounds very bizarre.
Yeah, so a bit of background here. So for ordinary matter, protons, neutrons, electrons, and so on, there are matter particles and antimatter particles. So the antimatter equivalent of the electron is called the positron. So it's another elementary particle. It has exactly the same mass as the electron. It has similar interactions to the electron, but it has the opposite sign of the electric charge. So it's positively charged rather than negatively charged. And when an electron and a positron meet, they annihilate usually into two photons, two particles of electromagnetic energy. And this is generally true. So most particles have distinct antimatter cousins. So there's antiprotons as well as protons, antineutrons as well as neutrons. Some particles are their own antiparticles. So the photon, there's no antiphoton, it's its own antiparticle. The Higgs boson is its own antiparticle. So they can either be the same thing or they can be different things. And when they're different things, it means certain things like electric charge are the opposite value between the two. And also generally, when a particle and antiparticle come together, they annihilate into something else. Often photons, it can also be neutrinos, but something else. So one of the great mysteries of cosmology, which is something I study also, is why the universe today is full of matter and very little antimatter. So all the stars and galaxies and the gas between galaxies and everything, planets, you and me, are composed of protons, neutrons, and electrons. Very little in the universe exists in the way of positrons, antiprotons, and antineutrons. But from the point of view of fundamental theory, these are almost, equivalent things. And, in the same way as electrons and positrons, when they get together, turn into two photons, you can also have what's called pair creation. So you can have, for example, two photons collide with each other and produce a positron-electron pair. In more energetic processes, you can produce a proton-antiproton pair. So in the very early universe, soon after the Big Bang, when all the evidence suggests the stuff in the universe was very hot, which means the average kinetic energy of the stuff was very high, you would expect pair creation processes to be occurring very, very rapidly, and the universe to be dominated by these sort of processes. So you're led to expect that the very early universe should be a 50% mixture of particles and antiparticles, okay? But the universe today is full of particles and very few antiparticles. So something happened, and the something that presumably happened is the universe may well have started, and this is the usual hypothesis, with an exactly 50-50 mixture of particles and antiparticles. But then for some reason, which we understand in broad terms, but we don't have a specific theory for that's been experimentally verified, a little bit more matter than antimatter developed. And you don't need much more. You need actually 1 part in 10 to the 10. That's what the data says. And then as the universe expanded and cooled, it became favorable for antiparticles to find a particle and to annihilate with that particle and to produce various kinds of radiation, primarily photons and neutrinos, if we're just talking about standard stuff. And I'll talk about what radiation is in a moment more generally. So, but because there was a little bit more matter than antimatter, the idea is eventually all the antimatter has annihilated away, and there's a little bit of excess matter left over, and that's got nothing to annihilate with. And because electrons and protons are stable particles, they hang around, and that's what forms the stars and galaxies and all the rest of the things we know and love today. And the remnant of the fact that there were almost a 50-50 mixture of particles and antiparticles in the early universe is precisely the radiation that we see in the universe today, the cosmic microwave background radiation, which is the remnant of photons that were around in the very early universe. And also there should be an equivalent background of neutrinos, which have been indirectly seen but not directly proven, because it's very hard to see them because they're very weakly interacting. So and we know that there are about 10 to the 10 times more photons in the universe today than there are matter particles. That's where we get the 1 part in 10 to the 10 from. So all of these are observational, established observational things. So if we're talking about the origin of ordinary mass in the universe today, it's a confluence of 2 things. One is the matter-antimatter asymmetry, this 1 part in 10 to the 10 excess of matter over antimatter. And the second thing is what we discussed earlier, which is the mass of the proton. So the 1 part in 10 to the 10 tells us basically how many protons there are in the universe today, because most of the universe is just hydrogen, so protons. And then the mass of the proton, then gives us the mass density of ordinary matter. So it could be something similar in the dark sector. It could be that the dark matter, that there's dark matter and dark antimatter, and just like protons and antiprotons and electrons and positrons annihilated in the early universe, also dark matter and dark antimatter annihilate and turn into something. And whatever that something is, it's got to be not very obvious to us today. And that means some form of radiation. Now, what I mean by radiation in this context is actually just stuff that's very light and moving very fast. So photons are exactly massless. So they're about as light as you can get, and they move at the speed of light, which is as fast as you can go. Neutrinos have a little bit of mass, but they're also very light, and at least some of them will be relativistic today. So that's what we mean by radiation. It's just stuff that is moving close to the speed of light, basically. And so it could be that in addition to dark matter, so just like ordinary stuff in the universe today has heavy stuff like protons, and then very light, fast-moving stuff like photons, which is radiation, it could be that the dark sector is similar, that there's kind of massive dark matter particles, but there's also an analog of photons, something that's moving close to the speed of light or exactly at the speed of light, and that would constitute dark radiation. So this is a rather exciting topic. A few years ago, about 10 years ago, there was actually some evidence that dark radiation existed because it would help to drive the expansion of the universe at certain times in the evolution of the universe. But these days, that evidence has gone away. And so actually, in theories where there is both dark matter and dark antimatter, and you need dark radiation, that actually, the non-observation of dark radiation actually acts as a constraint on our theories, and a very important constraint. So I think the discovery of dark radiation would be super, super exciting from the point of view of dark matter. And I was disappointed that the evidence went away.
Cool, thank you. There's a nice little chat going on with Geraint, Tamara, and Tim in the chat. Can someone explain what it's about? It looks very interesting.
I could jump in. So the question is about the creation of matter and antimatter today. So in our laws of physics today, when you have interactions, that you basically get, and I'm going to say basically because there are some asymmetries in the universe, equal amounts of matter and antimatter produced when you have reactions. So any reactions today, the net amount of matter stays the same because you get the same amount of matter and antimatter. But this difference between matter and antimatter that Ray mentioned, that was written into the universe in its earliest stages. So something happened before the universe was about a millionth of a second old that wrote in an asymmetry, which is now sort of, it's sort of hidden in the reactions that we have. And so that's one of the big questions that's still, with the birth of the universe and the Big Bang, we have to understand why we have a universe of something. Why wasn't the universe perfect? And essentially ended up with a universe of just radiation because all the matter and antimatter would have annihilated. So just mention that today, laws of physics seem more or less symmetrical, but in the early universe, there was something that happened that left us with matter in the universe today.
In fact, the situation is quite subtle because we know from just experiments done on planet Earth that matter and antimatter behave almost the same way, but not quite. There's something called, it's called CP violation in the technical jargon. It was discovered in the early 1960s and it was the subject of a Nobel Prize. It was actually a groundbreaking discovery. So there's a subtle difference in the behavior of ordinary particles and ordinary antiparticles. So that is one of the ingredients you need to understand how the cosmological asymmetry between matter and antimatter had to have arisen. But the hell of it is, the difference between matter and antimatter that we observe for ordinary things is not enough to explain the cosmological disparity. So one of the things that particle physicists do is search for new sources of CP violation, of differences in the behavior of matter and antimatter. And if ever they find a new source of that, that would be really big news, both for particle physics and also for cosmology. It's one of the things that there are big experiments being done on Earth, especially with neutrinos, that are looking to find a new source of CP violation. So with neutrinos, there are neutrinos and antineutrinos. And if matter and antimatter don't behave the same, you expect neutrinos and antineutrinos to oscillate amongst themselves at different rates, because that's one thing that neutrinos do. They transform into each other. And neutrinos and antineutrinos would do these oscillations or transformations at different rates. And there are big experiments being done on Earth trying to find exactly that. And as I said, I expect that will be confirmed at some point. There are already hints for it, and that will be big news and could have cosmological ramifications.
I'll pause there and just ask if anyone has any questions they would like to ask from that, or anything else at all. While you're thinking, there seem to be a lot of different explanations or models. What are the, I mean, there's some key ones. There's some great YouTube videos, which some of us probably watched when we were preparing for this. And if we're not in the field, we think, oh my God, that looks pretty compelling. And then other people go, oh, they're a little bit on the edge. So, you know, what are the out there models? Because, you know, for a lot of the people here who can't tell the difference between what's bunkum and what's has consensus to it, what are the ones that we can give some credibility to, and which ones are a little bit out there on the edge?
In terms of dark matter is notorious for having a wide range of different possibilities, all the way from particles which have hardly any mass, like ridiculously small masses, like 10 to the minus 22 electron volts, which is like stupidly small, all the way to primordial black holes with masses a few times that of the sun, which is a very different kettle of fish, and kind of everything or a lot of things in between. So some of them, I would say, at the edges are a bit out there, but in between, there are quite a number of reasonable candidates, and they're all under active study. So, you know, you've heard of things like WIMPs, weakly interacting massive particles, that sort of became the kind of most popular dark matter candidate amongst particle theorists. It was never my most popular candidate, but for most people it was. There's something called the axion, which is a bit hard to describe, but it's a very light particle that in a very subtle way could be the dark matter. And there are a lot of experiments being done to try to find that. There's something called sterile neutrinos, which remain as a dark matter candidate. Those are the sort of three main ones. And then the asymmetric dark matter that I was talking about, this is where there's dark matter particles and antiparticles. That's sort of my favorite. So, you know, I think those are four reasonable candidates, and things like supermassive primordial black holes and really, really tiny mass particles are sort of a bit out there, in my opinion.
I guess also in terms of dark energy as opposed to dark matter, the energy of the vacuum itself is one of the leading candidates. So quantum physics predicts that there should be vacuum energy out there, and predicts that if it exists, well, we've seen experimental evidence that it's there, that should have a repulsive effect in gravity. So it would accelerate the expansion of the universe. So it has the properties of dark that we want dark energy to have. The only problem is that I think we mentioned this last time, quantum physics also predicts how much of it there should be, or has a sort of a loose prediction for that, and that prediction is wildly off. It predicts way more than we actually see. So either way more or nothing. And so that's the leading candidate, and I'd be really excited if that was the explanation, because I feel like if a quantum theory of gravity can explain the amount of dark energy that we see, or the amount of vacuum energy that we see, and reconcile that with the predictions, then we have a beautiful candidate for what could be causing the acceleration of the expansion of the universe. On the slightly more far outside, but there's a bunch of theories that I really actually have some appeal, but are more out there. The entropic theories of gravity. I don't know what everybody thinks of these ones, but ones where gravity is not actually a fundamental force, it's an emergent property that comes from the collective behavior of particles of space-time type of thing, like this kind of concept. What those particles are and that sort of thing is all up in the air. But that would make gravity more like something like elasticity, where you can make a simple sort of law that says the more you stretch an elastic band, the harder the force pulls back. But if you want to explain it from a fundamental level, you have to go to like the little molecules inside the elastic band and explain the quantum physics of that to actually explain why the force has the value it does. And that would make gravity like elasticity that had a more fundamental explanation under it in some way like that. And that's something that is more, that a lot of people would be extremely skeptical about, but is another kind of theory that is popped up.
Another left field question that arises from that. When we were busy constructing the standard model, there was quite a lot of talk about gravitons and how the graviton was the particle associated with the gravitational field. It was supposed to have a spin of 2. String theorists were having fun with it. Where is that today, and how does is there a similar thing in dark matter? Are the dark matter particles going to be something like a graviton? It's going to be a particle which is associated with perhaps some kind of dark matter field. Are we actually talking about dark fields, or a dark matter somehow not related to fields, the way that gravitons are related to a gravitational field? Where do gravitons and dark matter particles sit with each other?
I'll jump in there. So gravitons are probably in exactly the same place they were when you read about them, in that they're hypothetical, right? Yeah. So we don't have a quantum theory of gravity, so we don't have gravitons other than as we hope that there's a particle that mediates the gravitational force. Now, when you talk about gravitons being related to fields, in quantum physics, all particles are related to fields. Yeah. Mm-hmm. Electrons are particles of the electron field, photons of the electromagnetic field, and if gravitons are particles, they would have an associated field as well. You can't write quantum mechanics in a way without having fields that describe particles. Mm-hmm. But there is no quantum theory of gravity. So as I said, it's probably where it was when you last read about it, and it probably is where it was when I read about it as an undergraduate in 1987. So, you know, the gravity and quantum mechanics are still, you know, sort of butting heads.
So is the structure of dark matter and dark energy similar? Do we have a dark field of which we consider or regard the dark matter particles to be perturbations or manifestations of a field? Is there a field theoretic view of dark matter and dark energy?
Well, dark matter theories are typically quantum field theories, just like the standard model of particle physics. Yeah. So yes, the same.
Okay.
As far as dark energy is concerned, I'd actually like to hear from Geraint and Tamara on that. What do you think of the idea that dark energy is a field rather than the cosmological constant, a field of some sort, and there's some sort of even modification of general relativity required to understand dark energy? Maybe not as bizarre as entropic gravity, but something else.
Okay, I'll jump in first. Look, there are going to be as many different views as there are going to be cosmologists on this, right? Because one of the problems that we really have with dark energy is that it only really exists inside our relativistic equations, right? So there's a term in there which is causing the expansion of the universe to accelerate. And of course, what we know is that general relativity over here is very distinct from quantum mechanics over there. So we get this picture of dark energy, which feeds into this equation, but it doesn't tell us anything about what this thing is, only what its sort of bulk properties are. In the same way as that we know the air in the room is made of molecules, but all I care about is the temperature, the pressure, the density, because that's what affects me. So we don't know. We don't know. And I have been in a pub and I have argued with people, and might even been with Tamara even, about which side of the equation do you write the cosmological constant on? Do you write it on the side where it is a substance, or do you write it on the side where it is geometry? And, you know, it has that freedom. And I don't think anybody would be willing to bet their house one way or the other. Anyway, let's see what Tamara says.
Yeah, that's a really good point. Like, for those who don't know the general relativity equations, you've got one side that has like sort of how gravity acts and stuff, and one side which has like the matter and the substances on it. And so how the substances react to how you get gravity from the substances and stuff is the essence of that equation. And where was I going with that? And yes, so that's the one of the really cool bits that we don't really know about where cosmological constant should go, or the vacuum energy should go. What was the original question? I've lost it already.
And what is it? Is it?
Fields.
Oh, yeah. How is it related to fields?
Yes, and yeah, very difficult to say. I mean, there's these cool scalar field models and stuff where, and some of these are used to explain a possible inflationary period in the early universe. And I've been to conferences where it was slightly disillusioning, actually, when people were going, well, what if it's this, what if the field takes this form? Or what if the field takes this form? Or what if the field takes this form? And it was just sort of like throwing ideas in the air about maybe it could be this, maybe it could be that, without having a really good fundamental sort of feeling to it. And one of the great things about relativity is that it's based on like such a sound philosophical principle. Like you basically require that the speed of light looks the same to all observers, and that the laws of physics should be the same everywhere, and relativity sort of pops out. The equivalence principle, and it's sort of necessary based on those sort of sound philosophical principles. And I think all of the theories that I've heard to explain dark energy, I feel like most are lacking that sort of sound, that sort of thing that makes you feel, oh, that feels really obvious, that must be the solution. And I haven't encountered that as an explanation of dark energy yet.
So can I ask my question in another way? So I'm aware that you cosmologists are trying to find or constrain a redshift dependence of dark energy. So the background here is the dark energy has a certain value, and if it's a cosmological constant, as per Einstein, it maintains that value forever. But it could be that it's more complicated and the value changes with time, which would make it not a cosmological constant, but more like a field. So Tamara, Geraint, if observations were to establish a redshift dependence of dark energy, what would you work on?
Do you mind if I go first?
Well, I'd work on explaining that redshift dependence. Why is it changing with time?
Yeah.
I would ask whether it's changing with time or with density. Like, is it a environmental type of effect because the universe was denser in the past, and like, is there a tracking between those things? It would open all sorts of cool new questions to try to answer.
Yeah, can I just add a subtlety there? I mean, one of the reasons that we're looking for the change of dark energy over the lifetime of the universe is because if dark energy is the cosmological constant, we are in the most maximally boring possible universe that there is, right? Because there's going to be this stuff underlying the universe. And again, we don't know if it sits on the energy side or the geometry side, and it doesn't do anything other than control the expansion of the universe, but it's just there. So the reason that we're looking for change is because that would mean that it does something more interesting and that there would be new physics defined. But I must admit, every time we take a measurement of dark energy, it just comes out looking like it's a boring cosmological constant so far.
Although one might argue that the maximally boring universe would be one without dark energy in it.
Yeah.
And I guess the question is also that we want to answer, is dark energy something that we can harness? Like, is it an energy of some sort that we can use? Who knows what we can do with propulsion systems, or like, anti-gravity things to get off the Earth or something, or those hoverboards that I was promised in Back to the Future. If we can harness these mysterious parts of dark energy and dark matter. I mean, there's a pretty solid chance that we're not going to be able to harness them in any way, but that understanding them fundamentally will allow us to do more stuff with the quantum technology and stuff that we can interact with more strongly.
Is the dark energy of maximal entropy? Because if it is most evenly distributed, then there won't be any way of extracting energy out of it and getting it to do any work, no matter how much of it there is. Is that a problem, do you think?
No. So things are only maximal entropy when they're uniformly distributed if you cannot get them to collapse.
Yeah.
So a cosmological constant, you can't get it to collapse. If it is something different, if you can get the leopard to change its spots, then it has potential. You could get it to do stuff by getting it to clump in various places. But we don't know. We don't know if it is the boring universe, then we can't do anything with it. It's just a sea of background.
Mhm.
But if it can potentially clump, then maybe, as Tamara said, you could engineer it and use it for warp drive engines or something, right? But we don't know yet.
Yeah, and the question of entropy is one of my favorites. It's a really interesting one, because the entropy that you're taught when you're in basic physics is that if you put a bunch of gas in the corner of the room, it'll spread out into the most homogeneous distribution it can, filling up the room, which is great because that lets us breathe, etc. All of that explanation is in the opposite sense to when you add gravity into the mix. Because if you add gravity into the mix, if you have a big homogeneous or almost homogeneous thing of gas, it will collapse and form a star or a galaxy. It'll gravitationally collapse, and the maximal entropy state is a black hole. So the maximum entropy per volume is the situation where you've got a black hole. So you want to be maximally clumped to have maximal energy once you've added gravity into the mix. So there's like some competing effects there. And I actually did my PhD on the entropy of the cosmological event horizon, which wouldn't exist if dark energy didn't exist. And so there's many cool entropy issues to discuss.
Okay.
Can I touch on something that Scott brought up and that Tamara was sort of discussing a little bit? There's a lot of different theories, and I can see that some of the professionals here talk about some of them with a smile on their face. What's the status in the community over something that is believable and realistic and something that is a wacky idea, but people are still getting funding to study it? How is that dealt with in the community?
Well, it evolves, I think. So I can talk a bit about dark matter from the particle physics community perspective. So the community for a long time was rather fixated on the idea that the dark matter had to be this thing called a WIMP, a weakly interacting massive particle. This is basically a single particle that is its own antiparticle, and it has a mass that's similar to it has a mass of similar to the W and Z bosons or the top quark, a pretty high mass, but not ridiculously high. And the weak part has to do with how strongly it interacts with other particles, and there was a reason for it to be weakly interacting. And this was favored because of a certain kind of paradigm in particle physics that was favored as being the next great big step forward, called supersymmetry, that some of you may have heard of. And this was meant to be discovered at the Large Hadron Collider, and it hasn't been. So, and WIMPs have been looked for in other ways independent of the LHC, and they haven't been discovered yet. So enthusiasm has waned a little bit for WIMPs. They're still around, and many people still like them a lot. But the effect that the experimental non-discovery as yet of WIMPs has had is to broaden people's minds and to start thinking about other possibilities, which I think is very healthy. I thought it was unhealthy for the field to be fixated on one idea. So for example, the axion, which I mentioned briefly, which is a complicated thing to talk about, but it was invented long ago, and it was known to be a dark matter candidate. And then it became forgotten about for quite a few years because everybody liked, not me, but other people like WIMPs so much. And now it's come back into fashion, you know, and there are all sorts of new experiments being proposed. And it's a really lively field of research, searching for the axion, you know. So that's an example of where I think the sociology of the field is healthier because the cherished ideas of many people have not as yet come to fruition.
So you think it's much better then to hedge your bets? Nobody really knows what it is yet. So hedge your bets, look through many different avenues,
That's
someone will get it.
That is my strong opinion. That is
Mm.
my very strong opinion. Some people may disagree with me a lot, but that is my very strong opinion. I mentioned that dark matter is notorious for being anywhere from very light particles to very heavy primordial black holes. That just tells you that we know so little about what it is that it would be, in my opinion, deeply unwise to put all of our dollars into searching for one kind of hypothesis, testing one kind of hypothesis. I think there needs to be a plurality of hypotheses and ideas explored. And hopefully one of them is right. You know, yeah, so, you know.
Would you liken it to football teams? That people find their team or their theory that they're gung-ho on, that they like, and they'll stick to their guns and follow that theory and champion that theory all the way through? Or do you feel that, you know, as you said, that the whole society maybe waxes and wanes depending on how the evidence is coming back?
It does. So, I mean, the great thing about science is we do experiments and we find out how the world actually behaves. And you might have a cherished hypothesis on whatever it is. But if experiments, say multiple independent experiments, unequivocally tell you that your cherished idea is wrong, then you have to give it up. If you don't give it up, you kind of become a nutcase. So I think the fact that we do experiments and we believe the data, or at least most of us, of course, the experiments have to be believable, and there's a whole discussion there about how you really establish things experimentally beyond reasonable doubt. But you know, once you have, you go with that, and you change your view.
There's a really good question in the chat here that relates to that from Tim, and that is there a feeling that we'll find answers to these questions by going bigger, as in astronomical, or going smaller, as in quantum?
I would say both.
Both. Astroparticle
Are there any
physics.
answers at all in this field?
Definitely both. I think you need to explain both. You need the quantum to explain what you see on the large scale. And one of the reasons looking at astronomy is so cool is because you can look at time scales and energy scales and length scales and stuff that you can't do on Earth. And that can inform the fundamental physics at the small scales. And so I think they're extremely complementary, and we need to look in both directions.
And we do. I mean, I'll give some examples. So the standard dark matter paradigm is called cold dark matter. And people like Geraint, can do cosmological simulations where they start off with a bunch of dark matter particles, have them interact under gravity in an expanding universe, and see how they clump, and then compare how they clump with how we see things clump in our actual universe. And there are issues with the detailed comparison of the simulations and observations for objects the size of galaxies. Bigger than that, everything looks fine. But for objects the size of galaxies, there are some issues. There are some quibbles about the agreement between strict cold dark matter and observations. These go by names like the core cusp problem, the missing satellites problem, the too big to fail problem. There are various issues of detail about agreement between calculations and observations. And this is an active discussion in the astroparticle community as to whether these discrepancies are real or just a function of the fact that we can't do our calculations properly, because things are complicated. But in principle, it is possible for, say, galactic scale observations to prove that strict cold dark matter is not quite right, and that there's a modification that you need to that. And then that would be very important information for particle physicists.
I had a follow on from what Kirrily's question was before as well, about the different types of theories and what gets supported in the physics community, because it's I think I completely agree with Ray that like diversity of viewpoints and attacking the problem from many different directions and looking for many different types of solutions is really important. And I often get contacted by people with, you know, with their theories or this, that, and the other. And there seems to be a perception in the community that physicists are very gung-ho on maintaining the status quo, that they don't want their theories to be challenged. And I think nothing could be further from the truth. Like every physicist who's doing research wants to challenge those theories and come up with the next big theory and, like, you know, show that they can improve on what has been done before. So basically every research physicist is out there trying to break our current theories, either by observing new things and finding things that don't fit with the theory, or coming up with new explanations, new theories. And so it's a very creative space to be in, much more so than a lot of people appreciate, I think. But one thing I would say is that if you come with a completely wacky idea that's like really far from left field, it will be difficult to get funding for that until perhaps you've established credentials as someone who appreciates the existing, what people have already figured out, and the pros and cons of the existing theories, before you sort of get the credence that someone will sort of I guess understand that you understand what's going on there, and then end up branching out into new things.
That it could be a real theory rather than just a crackpot idea. Yeah.
Now, before we run out of time, I noticed in the chat that Peter Lamb has asked that we noticed that we haven't talked about the problems with general relativity, and how the issue may be not with dark matter and dark energy, but somewhere on the other side with general relativity. What do we know about what problems are there with general relativity? I'm not even sure I know what they are.
I'm happy to jump in here. So there are no problems with general relativity. That is part of the problem. But so Einstein's general theory of relativity, which I'm teaching at the moment, is one of those theories which Einstein gave us this new picture of gravity, and we got a whole bunch of tests which have been tested over and over again: deflection of light by the sun, the Shapiro effect in the solar system, particles, light rays going up and down buildings, etc. And it works perfectly. The problem that we have is that Einstein set his theory by comparing to Newton. So what he did was saying that his theory had to reproduce Newton's theory of gravity in the appropriate regime. Now, the problem is that you could have other parts to the general theory of relativity which become irrelevant when you go down to the Newtonian theory, but are still important on the larger scale universe. So the question is there something missing from general relativity when we go to very large scales in the universe? That's really what the question is all about. In the solar system, we know that general relativity works really, really well. On Earth, it works really well. If it didn't, our GPS wouldn't work. We'd all get lost trying to get to parties, etc. But are there terms which become important when our scales become the scales of galaxies and then to the scale of the universe? And the problem is that we have an equation, and there are an infinite number of ways to modify that equation. And there are many, many ways those modifications can sort of look like they explain dark matter and dark energy. But so far, there is no one overall consistent extension to relativity that can explain everything that we can see. So at the moment, taking general relativity as it's currently formulated and adding dark matter and dark energy works better than any of the modifications that people have tried to introduce to say, oh, we need to fix relativity. That's where the problem is.
Okay.
And
Scott, Geraint, can I come in there? Because you have heard me talk at the Sydney Institute of Astronomy some 6 or 7 years ago, and I've known Ray for 8 or 10 years. I've tried to communicate with Tibor and with Tamara. I think we're overestimating the fact that another theory can't reproduce the predictions of general relativity. And also I dispute that there are no problems with general relativity. For example, a necessary consequence which the Nobel Prize was awarded was that it necessarily leads to singularities. And when I grew up, a singularity was a division by zero, and it was unphysical, and it indicated that there was a problem with the theory. For example, it also predicts dark energy, dark matter, and I think they're real problems.
Sorry, can I jump in a little bit there? I mean, dark matter and dark energy are distinct from Einstein's general theory of relativity, right?
Yeah, they're ad hoc hypotheses based on
observations, right?
Yeah, but analyzed within the context of general relativity.
Correct. So you either say that I'm going to say that there's stuff in the universe, or I'm going to say that I need to fix up the equations of relativity. And as of yet, this side of give me a new relativity that can do it doesn't exist.
I disagree.
And I would politely disagree as well, because if there really was that could explain everything, then I would be teaching it today.
But perhaps you haven't considered it.
Okay, so
all right. I'd like to talk. If I can, just to give my background, I studied elementary particle physics at Melbourne Uni. I did my master's there, and I left that because my supervisor was leaving, and I gained a scholarship to Oxford. So I did my doctorate there in elementary particle physics. But then, Scott, I had a 27-year career at CSIRO, and it's only recently that I've been able to come back to fundamental physics. The where I got led on this was that the original expectation was that a photon would not lose energy in escape, would not be affected by a gravitational field. Yet under general relativity, it's accepted that we go to the Pound-Repka experiments where they sent a signal from a crystal up to a matched crystal and down again, and found that there appeared to be a redshift of the light. Okay, the gravitational redshift. You agree, Geraint, that was the conclusion?
Yep, I do.
Yeah. Well, the alternative is what many people who are advocates of general relativity say is that it's not the photon's energy changed, it's the energy of the receiving atoms. The consequence of that is that they have a blue shift, so their energy is increased. And so it's not photons that's changed that are susceptible to the environment. The speed of light is constant for photons. When there's no gravitation, but it's the background affects the speed of photons, and it affects the mass held by matter. If you allow that, it seems like an enormous contradiction, but you can reproduce the predictions of general relativity without the problems of dark matter and dark energy.
But Peter, is this a difference in the theory, in the formal formulation of the theory, or is this a difference in the way we might interpret the theory? The theory is the same theory, we're just interpreting it differently.
Yeah, there's the maths works out very similarly, and I've tried to explain that. But no, the theories are fundamentally different in that the speed of light is not constant and mass is not constant. If in fact mass can vary according to the density of surrounding matter, which shouldn't be surprising because it's the changing density of surrounding matter that gives rise to gravity, then mass is not constant, and that will automatically lead to an apparent dark energy. And you can turn it around and say, if the speed of light varies in this way with the redshift, then you completely remove the accelerating expansion. The behavior is constant within errors, so that there's no need for an accelerating expansion. It's a bit more complicated what you have to do and postulate to get rid of dark matter. I hope I was saying dark energy before. Dark matter can arise from an asymmetry in the background of matter and antimatter, and that can actually vary, because if the regions of matter and antimatter are separated, they can give a very uniform background. Because another consequence of this, and I'm jumping around, is that this necessarily requires gravity to depend on the total background, not the gradient in the background. We only see the effect due to the gradient, but there's actually an enormous background from the rest of the universe, because the gravitational potential falls off as 1 on r, not 1 on r squared. So the gravity of the distant galaxies dominates. So there's a huge background.
Peter,
but yeah.
I realize that I know that we're actually 100% out of time now, but there was also another question in the chat that I was wondering we could get to before we got to the end.
Yeah.
Am I allowed to take 30 seconds to try and answer that?
Yeah, look, I just wanted to put it out there that I believe, and I'm happy to talk about it. Can I put in a plug that you can find it on www.fullyrelative.com, and it is continually being revised. There are mistakes there, and I'm trying to get rid of some of them. I'm trying to write this up in a simple, understandable way. But I really genuinely think there is an opportunity out there, and I'd love other people to contribute and criticise.
Thanks.
Thank you.
Thanks.
Thanks very much for your listening.
Can I take 30 seconds, moderators? Because Neil's question was, if we're living 5 billion years ago, when the expansion of the universe was slower, is it likely we would be making the same discoveries, all things equal? And I think the answer is definitely no. It might be harder to see dark energy, for example, because we wouldn't be seeing the universe accelerating in the way that we see it now. But I think the more interesting question is, what if we lived 100 billion years in the future? Would we be able to figure out that the universe had a beginning even? Because we wouldn't be able to see the cosmic microwave background. We wouldn't see other galaxies moving away from us because they would all be beyond our horizon. We wouldn't see them. We'd look like an isolated clump of galaxies. And would we be able to figure out that the universe even had a beginning? So I love the question of, what does our place in time limit us from understanding about the universe as a whole?
Yeah, that's terrific. It's a very interesting point that basically everything that we understand is perspectival. It's relative to where we are and when we are and what we experience, because as we said at the beginning, we infer the world from what we observe. So clearly we're limited by our observations. I've got one very simple last question, perhaps to Ray. If at the very early universe, if the particles condensed out of whatever primordial soup of energy there was at the moment of the Big Bang, are we again modeling the dark matter condensed out of that same primordial soup, or are we somehow imagining dark matter to have a different source, different origin?
In general, so the soup is basically the particles all moving around. So it's sort of not a question usually of particles condensing out of a soup, but the particles are the soup, and dark matter particles would be one component of the soup. Where you could have something more like a non-particle soup is at the end of this period of cosmological history called inflation, for which there's a lot of circumstantial evidence, but not quite proven. And there, so inflation is a brief burst of exponential expansion, a bit like the dark energy dominated phase we seem to be entering now. But this was a very temporary exponential expansion of the universe that is needed to solve certain important problems in cosmology, theoretical problems in cosmology. And but this exponential inflation at some point has to end. And then when it ends, the energy from that expansion goes into particle creation. So that's where you sort of get particles created out of a soup. And in most cases, you would expect dark matter particles to be created in the same way. It doesn't have to be, but mostly it would be. The details of that is all very obscure because specific theories of inflation don't really, we don't really know what specific theory of inflation we're talking about. It's more like a general idea. But so it could be that dark matter and ordinary matter was created at the same time from the inflationary soup, or it could be that dark matter was created first and then ordinary matter sort of was created from dark matter, or vice versa. I think all these things are possible at this point.
Okay, well then please disabuse me of my misunderstanding. I thought that at the moment of the Big Bang, there was only energy. The universe started as a ball of energy, as I've heard said, and that the particles came out of that energy.
You were lied to, Tibor.
Sorry?
You were lied to.
Oh, okay. All right. So the Big Bang actually created the particles as well as or created particles as well as energy, or what actually came out of the Big Bang? What was the first product of the Big Bang?
Well, this is like another session.
Unfortunately, I think it might need to be another session.
Yeah.
So
could we just say that nobody knows? I mean, that's essentially it, right?
Yeah. That would be the zeroth order. Right?
Good answer.
I accept that. Very good.
Thank you very much. I think that's a really good point to bring it together. Like many of these sessions, it takes a little while, and the most juiciest part of the hour and a half is actually the last 25 minutes, and that's happened again this time. Can I thank our panel, Tamara, Ray, and our permanent panel, Kirrily, Geraint, and Tibor, and thank you also Peter as well for chiming in there as well, and putting a very different perspective on the conversation as well.
Thanks.
So I'll put this recording up, and so you can watch it again and take notes, and maybe we'll need another session in the next year or so when we maybe come back and revisit this topic. So thank you very much, everyone. We will have another Zoom into Physics in October on the 27th, again at 8 p.m. And at the moment we're playing around with the topic a little bit, but I think we're starting to converge on what's physical about physics, what makes science scientific, and really trying to play with the concept of the distinction between science and pseudoscience. So I think that's going to be quite good fun, although I'm not quite sure what it actually means yet, but that's the fun of it, right? So thank you very much, everyone, and enjoy the rest of your evening, and hopefully see you back here in October.
And thank you, Scott,
Thanks.
for organizing this.
Yep.
See you
Bye,
all.
everyone.
See you.
All.
See you.